Hey everybody. So in this class so far, we've learned about matrices and we've learned about linear transformations. And one of the big results is that there's this relationship between the two where you can go back and forth. If you have a linear transformation, then you can get a matrix that corresponds to it, and vice versa. And each side of this correspondence brings its own perspective that can be useful in different contexts. And in particular, we can think of linear transformations as being similar to functions in the sense that you plug in some kind of input and you get some kind of output from it. So something you know about functions is that there's this interesting operation you can do with functions called composition. And the way that works is that if you have two functions f and g, you can get a new function, which is sometimes denoted like this with a little circle, f circle g. But the right way to say it out loud is just to say f composed with g. And this is defined by the formula that f composed with g of x is f of g of x, which means that you plug g of x into f. So for example, if f of x is e to the x and g of x is x squared, then when you plug g of x into f of x, you get e to the x squared. And so f composed with g of x is e to the x squared. So there's a nice schematic way of understanding this, which is that say you start with x, and then if you apply the function g to x, you sort of think of g as a process, then that produces g of x as the output. And then you could apply the function f, which would produce f of g of x. And then f composed with g is the function which shortcuts this process and does it all in one step. So before going back to linear transformations, I feel like it'd be useful to say a little bit about how compositions of functions can be useful. So suppose you wanted to solve an equation like e to the x equals 5. What would you do? I'm guessing that you all know how to do this. You take ln of both sides, and the ln sort of cancels out the e to the x, and you just get x by itself. And so x is equal to ln of 5. So why did that work? How did you know to take ln of both sides? Well, the reason was because ln and e sort of canceled out. But that's just an informal way of saying something about compositions of functions. So to be more specific, we could look at the function e to the x, and then we could compose with the function ln of x. And then we know that this composition is just equal to the function x. And it's that relationship that allows us to solve for x. So the point is that composition of functions gives us more algebraic tools for solving equations. Okay, so now let's get back to linear transformations. And suppose we have a linear transformation t from Rm to Rn. And suppose we have another linear transformation s from Rn to Rk. So similar to what we did with functions, it can be helpful to describe this schematically, where we think of t as being a process that goes from Rm to Rn, where if you have an m-dimensional vector x, you can plug it into t, and then you'll get an n-dimensional vector, t of x. Note that I'm not just keeping track of the individual vectors anymore, but I'm also keeping track of the entire spaces that t goes to and from as a transformation. We didn't do that with functions because for functions, it's always just real numbers. But now we have to worry about, is this an m-dimensional vector? Is it an n-dimensional vector? And so we need to keep track of that as well. So now we could do a similar schematic for s, but more importantly, we could compose s with t. Note that in order to do this, it's important that the dimensions match up in the sense that the output of t is the same dimension of vector as the input of s. But as long as that's true, then we can do this composition, which would be s composed with t. Now, I claim that s composed with t is linear. And to prove it, we just need to check that the conditions for linearity are true, using the fact that we know that s and t are linear, so they satisfy the conditions on their own. So for example, let's look at s composed with t of x plus y. That's equal to s of t of x plus y, because that's how compositions work. And now we can use the fact that t is linear to break up t of x plus y, and then use the fact that s is linear to break it up further into s of t of x plus s of t of y. And that is s composed with t of x plus s composed with t of y. So that shows that s composed with t is compatible with addition, And we can do the same thing with scalar multiplication. That's even simpler because you can pull the scalar out of t and you can pull the scalar out of s as well. And so it just pulls all the way out. Here's the detailed calculation. You can press pause and go through it step by step if you want. But that's the whole proof. All right, so far we've been talking about linear transformations without talking about the matrices that they correspond to. So let's bring those matrices into the picture now. So let's say that A is the matrix that corresponds to the linear transformation S. And note, since S was supposed to be a transformation that goes from Rn to Rk, A should be a matrix which can be multiplied by n-dimensional vectors and would produce a k-dimensional vector as the result. And so that means that A is a k by n matrix. And then in the same way, we'll let B be the matrix that corresponds to T. And so B would be an n by m matrix. And now here's the really interesting part. The fact that we can compose S and T to get a new linear transformation means that there should be some way to combine the matrices A and B together to make a new matrix. And whatever that way is of combining matrices, we're going to call it multiplication. So remember that there's this flawless dictionary between matrices and linear transformations. And we have this really natural thing that we can do in the world of linear transformations, which is that we can compose them. So there has to be some corresponding thing that we can do to matrices, and we're going to call that matrix multiplication even though we don't even know how to do it yet. We know that it exists, and we know that it's going to be useful because composition of linear transformations is a useful concept. But of course, we should ask the question, how do you compute it? So let's figure that out. All right, so our starting point is this equation, which says that the matrix product AB is the matrix that corresponds to the composition of linear transformations S composed with T. Now we don't know what A times B is yet, but we do know what S composed with T of X is. That's just S of T of X. And now we can use these formulas for S and T, where S of X is A times X and T of X is B times X, and substitute in. And so we end up with A times B times X, which might seem like it's not really any different from what we started with, but it actually is because the parentheses are different. And this we know how to do because we know how to multiply a matrix times a vector. And so when we do B times X, that's multiplying a matrix times a vector. The result is another vector, and then we know how to multiply A times that vector. So this we know how to do. We didn't know what A times B was because we didn't know how to multiply two matrices together. But now we have a formula that tells us how to do it, at least in principle. And now we can use this formula to figure out how to do it in practice. So we're going to do this by using a fact that we learned earlier, which is to find the columns of a matrix, you multiply it times these special vectors, e1, e2, and so on. And that will give you the different columns of the matrix, and then once you know the columns of the matrix, then you know the matrix. And maybe just to let you know, this process of deriving this formula, it feels pretty abstract because we're doing it for arbitrary matrices A and B. But in the end, we're going to end up with a way of calculating the matrix product that is very straightforward, where you just multiply certain numbers together. And there are a lot of books where they just start by telling you, here's how you multiply matrices, and they just tell you how to multiply the numbers together and get the product. But then you don't get any sense of where the product comes from. Why are you doing it? What does it mean? And so I'm hoping that by starting with linear transformations and compositions of linear transformations and then deriving the product very carefully from that rule, you'll have a sense of where the formula comes from. Okay, so what is AB? Well, we're going to learn how you can calculate it column by column. So from what I just said on the previous slide, we know that the first column of AB is AB times E1. And then from the work that was done on the previous slide, we can rewrite this as A times B times E1 with the parentheses changed. And now we can use the fact that b times e1 is the first column of b. And now this gives us a good way to calculate it, because you can take the matrix A, multiply times the first column of B, and then that's going to give you the first column of AB. And then everything works exactly the same for other columns. You just use the other columns of B to get the other columns of AB. All right, so here's an example where you can see this put into practice. So suppose we want to multiply these two matrices together. The rule that we just found says that we can do this column by column by taking the matrix on the left and multiplying by the different columns of the matrix on the right. So when we multiply the matrix on the left times 3 minus 2, we get minus 1 times 3 plus 2 times minus 2, which makes minus 7. And then 5 times 3 plus 4 times minus 2, which makes 7. And then 2 times 3 plus minus 3 times minus 2, which makes 12. And that's the first column. And then to get the second column, we would multiply the matrix on the left times minus 2, 1. So I recommend that you press pause right now, do it yourself, and then I'll put the answer up in a second. And there you go. So this is how you multiply matrices, and more importantly, this is why you multiply matrices, because you're really computing compositions of linear transformations when you do it. I encourage you to just do a few examples. You can just make up numbers for matrices and multiply them out just to get the hang of it, because it's the sort of thing that you're going to want to be able to do fairly quickly to where it feels like it's, a routine process for you. But there are a couple of warnings that are worth mentioning. So first of all, it's important to remember that the dimensions need to match up. It's important that the matrix on the left has the same number of columns as the number of rows of the matrix on the right. So in the example I did, the matrix on the left has 2 columns, and the matrix on the right has 2 rows. And that matching up was necessary in order to be able to multiply matrices. If those numbers don't match up, then you can't multiply. So for example, if I try to take the same 2 matrices and multiply them the other way around, it doesn't make sense, because then you'd have the matrix on the left with 2 columns and the matrix on the right with 3 rows, so they don't match up. So that leads us to another warning, which is that matrix multiplication is not commutative, in the sense that AB is not usually equal to BA. I mean, we just saw an example where AB makes sense, but BA doesn't even make sense. So that can happen, but even in the cases where they both do make sense, they're usually not equal. So that's some bad news, but I'll finish up with some good news. One thing is that matrix multiplication is associative, so it doesn't matter what order you multiply in, as long as you preserve the left to right order. And I'll point out that this is something that would actually take some work to prove if you were using just the rule for doing the calculation for multiplying matrices. But if you think in terms of linear transformations, it's almost immediate, because composition of linear transformations is associative. It doesn't matter what order you perform the composition in. When you compose 3 things, you're just doing one thing and then the next thing and then the next thing. So this is a case where knowing the relationship to linear transformations really helps us to understand things about matrix multiplication. And then another piece of good news is that distributivity holds, which is where you multiply a matrix times a sum of 2 matrices, you can distribute over that sum. So what this tells us is that matrices are convenient because a lot of the algebra that you're used to doing still works for matrices. But there's also some algebra that you're used to doing that doesn't work for matrices, and so you have to be a little bit careful. And learning about what you can and can't do is one of the important things that you need to be able to do when working with matrices.